Our lesson today will be angle units of measures. So we'll be focusing on the circle, and in particular we're going to be measuring angles in a circle. You're probably used to angles measured in degrees. We will be introducing another unit of measure called the radian, and we'll be essentially converting from degrees to radians, then from radians to degrees, and we'll look at some interesting applications of such. Right, so let's get into it. So you all recognize this to be a circle, and you know what the center of the circle is. Now, if we draw a radius there and another one here, so we end up with an angle here which we call angle theta. Now that is called a central angle. Okay, so that angle is said to be in standard position. Okay, so what we're going to be doing very shortly is now to introduce the idea of a radian. All right, so we know that if we have a circle and we go around the circle once, then we have 360 degrees. So that's what you're used to. You're used to the angle being 360 degrees in a full circle. Now this is also called one revolution. All right, that's actually another way of measuring an angle, a revolution. Just to sidetrack for a bit, if you realize that this is actually a conversion factor, so we could form a unit factor from this as we have done in the past. So we could say 360 degrees over 1 revolution is the same as 1 revolution over 360 degrees, in case you're being asked to convert from degrees to revolutions. But our focus now is going to be on the radian. So what is a radian? Let me go over here and show you what a radian is. If I have a circle, the circle has a particular radius. So that's the radius right there. Now, if I were to mark the radius off on the circumference, that's an arc. So this arc length is actually now a radius right here, from there to there. If that's the case, then this angle here, theta, is 1 radian. 1 radian. Sometimes we write it as 1 rad. So that's 1 radian. So the question then is, how many radians are there in 360 degrees? Well, we know that the circumference of a circle is 2 pi r. So since a radian is the degree subtended by the length r on the circumference, so if we take c and divide by r, we get 2 pi. So this 2 pi tells you how many radii are there in the circumference, or how many radians are there in 360 degrees. So the answer is 2 pi. So we know that 360 degrees here, as we said, from here, is the same as 1 revolution, which is now the same as 2 pi radians. Let me write it out, I-A-N-S. So that's going to be important. All right. So again, from here, we know that 360 degrees is 2 pi radians, and from this we could form, and we're going to be doing this later, but I'm just sort of giving you a sort of preview of it. We know that 360 degrees over 2 pi is the same as 2 pi over 360. But of course we could reduce these to 180 over pi. It's the same as pi over 180, and that's degrees, degrees, that's radians, that's radians. And we'll be using this later on to do some conversions, right? Now another thing we have to look at here is degree, minute, and seconds. So let me talk a little bit about degree, minute, and seconds. So we know that we know what 1 degree is. A degree is just 1/360th of the full circle. So that's 1 degree. Now think of an hour in terms of time. An hour can be divided into smaller units. Because if you're measuring, for example, how long it takes Usain Bolt to cover the 100-meter, he probably does it in 2 seconds. But it makes no sense to measure it in hours. That's just too long. So you use a smaller unit. You don't even use minutes, you use seconds, right? So in the same way, sometimes a degree is just too big a measure to measure an angle. A unit, I should say, to measure an angle. So if you take 1 degree and divide it by into 60 parts, what you get is called 1 second, and we write it as, 1 minute, sorry. Let me go again. You take 1 degree, divide it into 60 parts, you get 1 minute. So not the time a minute, it's an angle minute, and it's written as 1 with a little dash there. So therefore we know that 60 minutes equals 1 degree. Okay, so that's something for you to remember. Now, sometimes even the minute, the 1 minute is just too much, too big. So if you divide your minute again into 60 parts, you get 1 second, which you write as 1 with 2 little bars there, so it's 1 second. So therefore we know that 60 seconds equals 1 minute, and that's important to remember. So likewise, if you multiply 60 by 60, you get 3600 seconds, which would be equal to 1 degree. Right, so now that we've talked about angles, different ways of expressing angles, we said that there's radians, there is degrees, but we further divided the degree down into what we call degree, minute, seconds. So when you see DMS, it means degree, minute, seconds. What we're going to be doing now is to convert what we call decimal degrees to degree, minute, and seconds. If you look at this example here, it's 33.48 degrees. We want to get this to degree, minute, and seconds. So what we're going to be using is our conversion factor. So we remember that 1 degree is the same as 60 minutes. We also know that 1 minute is the same as 60 seconds. So from these we could form unit factors, right? So if you have forgotten what unit factors are, then you should go back and do a quick review, because that's going to be our assumption here moving forward. So let's do this one. There are 1, 2, 3, 4 here, but I'm only going to do 2. The solutions are posted on your D12. So, you do 1, you do all, but let's just do 2. So this first one says 33.48 degrees. Now, keep in mind that the DMS are whole degrees, whole minutes, and whole seconds. So what's not going to change is our 33 degrees. That won't change. But now we have to convert the 0.48, which is less than a degree, to our minutes and seconds. So what we do here, we're going to take 0.48, and that's degrees, and we are going to convert that in the first case to minutes. Well, minutes, we know that 1 degree is 60 minutes. We have degree in the numerator, so now we use our unit factor and we have the degree in the denominator and the 60 minutes there. So we see that our degrees will go, and then we now multiply our 0.48 by 60, and I'm doing this as we go along. Now once we do that, we get 28.8. And remember, now we are in minutes, so that's minutes. Now we said that the DMS are whole degrees, whole minutes, and whole seconds. So we're going to take the whole minute part and put it right here. So that's 28 minutes. Now we're left with 0.8 of a minute. So we take our 0.8 minute. We want to now convert that to seconds. So again, we're using the 1 minute is 60 seconds. We have minute in the numerator, so we want 1 minute in the denominator. So we have 60 seconds there. So the minutes go, and we take our 0.8 and multiply that by 60, and we get 48 seconds with no remainder. So now the 48 seconds, we move right here, we get 48 seconds, and that's our answer. So we know that 33.48 degrees is 33 degrees, 28 minutes, and 48 seconds. All right? Now, as I said, I won't do these two here. I'll leave that for you to practice. Nothing new there. So let me go and do this last one for you. Same thing. So again, we want to convert this to degree, minutes, and seconds. So we know that the 312 degrees will not change. Right? So what we do now, we take the 0.53 degrees, so it's 0.53 degrees, and we multiply that by a unit factor. Remember, we know that 1 degree, well, let's go, 1 degree here, 1 degree is 60 minutes. So we want to convert the 0.53 degrees to minutes. So degrees in the numerator, so we have 1 degree there and 60 minutes there. The degrees go. We multiply our 0.53 by 60, and we get 31.8. So 31.8, and this now has to be minutes. So we take the 31 minutes, we put there, and now we're left with 0.8, 0.8 of a minute, and we have to convert that to seconds. Well, again, we know that 1 minute is 60 seconds, so we want our minute to be in the denominator and our 60 seconds to be in the numerator. The minutes go, and you end up with 0.8 times 60, and again we end up with 48 seconds, so we put our 48 seconds there, and then that's our answer. Now we're going to be going the other way around. You're going to be given degree, minute, seconds, and now you want to go to a decimal degree. Right? So let me give you the method here. So if you're given your degree, whole minute, whole seconds, you leave your degree there, you add to that whatever value you have for minute, and you multiply by 1 degree over 60 minutes. That's your conversion factor. Then you add to that your seconds, and then you multiply by the conversion factor, which I told you earlier on, 1 degree over 3600 seconds. So this unit factor here will convert the minutes to degrees. So all of this here now, all of this here is now in degrees. And here, this unit factor converts your seconds to degrees. So all this now is going to be degrees. D-E-G. All right, so let's do one example for you. And that should be it. Let's do this example here. So what we have is 23 degrees, 15 minutes, and 30 seconds. So it's going to be 23 degrees plus we take the 15 minutes, you multiply by 1, the unit factor, 1 degree over 60 seconds, and then you add to that your 30 seconds, and you multiply by the unit factor, 1 over 3600 seconds, and that's degrees there also. Now you simply plug this in your calculator. You just enter 23 plus 15 divided by 60. You don't need the 1 over 60. You could simply, let me just do this again. You could just simply write this as 23 plus 15 over 60, and then plus 30 over 3600. And then all this is going to be in degrees when you're done. So if you do that, you should get 23.2583, repeating, and that's degrees. However, as you have learned, with rounding, you round this to the nearest tenth. So it's going to be 23.3 degrees. At this point, let me talk a little bit about rounding. Okay, so let me just use this spot here and tell you a little bit about rounding for this part of the course. Now, this is from your textbook. All right, so from your textbook, when you have lengths and the length, right, or angles measured in radians. So whenever you're rounding lengths or angles in radians, then you round to 3 significant digits, right? However, when you have angles in degrees, then you round to the nearest tenth. That is 1 decimal place. So that's why we rounded this to the nearest tenth. It's coming from here. So let's call this 1 and 2. So those are the rules for your textbook. Now, as far as we are concerned, so I'm going to say at Fleming, or for this course, I should say, we always round. So yeah, so we round based on accuracy. And accuracy of what? Of the original measurement. So generally we will stick with this, but there are times that this doesn't apply and you have to go back here. For example, the example we just did, right? We are converting this degree, minutes, seconds to decimal degrees. So you see, if we were to try to use the Fleming or our coarse rounding, the original is 23 degrees 15 minutes and 30 seconds, so there are no decimals there. So in that case, we have to revert to our rule for rounding angles in degrees. That's in degrees, so we round to the nearest tenth. And now we're going to be looking at radians and degrees. We'll be converting from radians to degrees and degrees to radians. I sort of alluded to that at the very beginning when I said that the circle is 360 degrees, which is the same as 2 pi radians. Now this can be reduced. If you divide both sides by 2, then you get 180 degrees. It's the same as pi radians. So from this conversion, we could form two unit factors. The first one is 180 degrees over pi radians, and the other is pi radians over 180 degrees. So these are the factors that we will be using to convert from degrees to radians and radians to degrees, right? And we know how to do this, because when would we use this first one? Well, radians in the numerator, in the denominator, sorry, radians is in the denominator. So if we want to go from radians to degrees, right? So this is used when you're going from radians to degrees. Now on the right side here, we have degrees in the denominator. So this is used when you're going from degrees to radians. It's as simple as that. So it's the same method. So if you, which is why we sort of try to encourage you to learn this unit factor conversion, because it's going to be useful. Sometimes we teach things and you could say, well, why am I using that method? Because there's another method, an easier method I know or I've been using all my life. But sometimes you have to sort of trust us that we know what's coming up, and maybe the method that you learned has some restrictions. So you have to try to have a little bit of trust sometimes. All right, so now let's do some problems here. Now, one other thing, whenever you see a angle in radians like this, express radians, you see a pi involved, then we say that this is like a pure radian measure. And if you see this, it's actually called like a decimal radian. Now how do I get this number here? I simply multiply 2 times and you press your pi key and you get this. This is obviously rounded. Alright? Or pi radians is 3.14. That's the approximation for pi. It says use your pi button. Always use your pi button on your calculator. Do not round off your values for pi, otherwise you're going to run into no ends of problems. Alright? So now let's do one or two examples here. So what we have is 30 degrees, which we want to convert to radians. So we multiply by that unit factor, that's a pi and 180. So because we have degrees in the numerator, we want to have the 180 degrees there and the pi radians right here. RAD. See, that's coming from right here, the second one here. All right. Now, we can, if you just use your fraction calculator, if you see that this is the same as 30 degrees over 180 degrees times pi radians, this is the same as that. Now, you could either put 30 over 180 using your fraction button, or you just know that 30 into itself, 30 into 180 is 6, so it's going to be pi by 6, or 1/6 pi radians. So now this is your pi radians, right? This is now in pi radians, your answer. This is what I call pure radians here, right? But let's not stick with that. Let's just call it pi radians. In pi radians, and this is actually pure radians. So let me make a correction there. So that's pure radians, and over here, when you see this one, that's called pi radians. All right. So pure radians is when you have the decimals. I think I got it the other way around earlier on. My correction. So pure radians is when you have the decimals, and pi radians is when you have the pi there. So this is now in pi radians. Now we could get this to be pure radians by pressing the pi button and dividing by 6. So if we do pi and then divide by 6, then we get 0.52359 and a bunch of other things. But again, remember that when you're rounding your decimal degrees, you round to one decimal place. So therefore, this will be just 0.5 radians. Right, so our answer is either pi by 6 or 0.5 radians. Right? So that's all there is to that one. And of course, you could try those examples. So again, right here, that's your pi radians and that's your pure radians. So pi radians could be something like 3 pi by 2 radians, and your pure radians could be something like 5.128 radians. I'm emphasizing this because I gave you the wrong information earlier on, right? So I'm emphasizing this so that it should be very clear. So again, pi radians is when you have the pi in it, and pure radians is when you have your decimals. If you're given radians, we simply multiply by the unit factor. Now we have radians in the numerator, so we want our pi radians here and the 180 degrees there. All right, so that's the factor. So in this case, we have pi by 4 radians. We have to multiply by the factor 180 degrees by pi radians. Well, right away you see that the pi's go and the radians go, so you're left with 180 divided by 4. 180 degrees divided by 4, which is just 45 degrees. All right. In this case, we have 3 pi by 2 radians. Again, we multiply by the unit factor 180 degrees by pi radians. Again, the pi radians go. You're left with 3 times 180 divided by 2. You could plug this in your calculator, or you could say 2 into 180 is 90 degrees, and then 3 times 90, it's 270 degrees. Now the third one, notice that this is now in pure radians. So you do the same thing, 1.75 radians, you multiply by the 180 degrees divided by pi radians. Now there's no pi to cancel, but you could certainly get rid of your units there and you're left with degrees. Now if you plug in your calculator, 1.75 times 180 divided by your pi button, do not put 3.14 or any such thing, enter the pi itself button, and if you do that, you should get 100.2676 and a bunch of things degrees. But again, based on our rounding rules, we round to 1 decimal place. It's going to be 100.3 degrees. So now let's move on to finding what we call the arc length and the area of a sector of a circle. So let's see what arc length is first, then we'll talk about the sector after. So if we have a circle there with center here, and we have a length along the circumference, so that's right here we have this length. I'm going to call that length S, so that's the arc length. Now this arc length is contained by a central angle theta. So we're going to try to find the length of the arc S in terms of theta, both in radians and in degrees. So let's try to do that. We'll do this using what we call a proportion, right? So we're going to say that the arc length S is to the whole circumference, which is 2 pi r. The arc length is to the circumference in the same way that the angle theta is to the total angle in the circle. So in terms of radians, it's going to be 2 pi radians, right? From this, we could say that S then is equal to the product of these two, which is 2 pi r theta. Then you divide by the 2 pi. The 2 pi goes, and you're left with just r times theta, where theta is in radians. So from here we could say therefore that if the central angle is in radians, then the arc length S is just equal to r times theta. Right? So that's one formula there. Now, how do we get it in terms of degrees? Well, we could do it in the same way. We could say we could also set up a proportion again and say that the angle here, theta, is to 360 degrees in the same way that the arc length S is to the circumference 2 pi r, and we want to find what S is. So S is going to be those two, so S is going to be theta times 2 pi r divided by 360, Now 2 into 360 gives us 180. So we end up with r times theta, and then so the r there, the theta there, then we end up again with pi by 180. And that's there in degrees. Now it's interesting that you see a pi by 180 here. That's a conversion factor that goes from degrees to radians. So another way of doing it is to take this formula here. We could say that S is equal to R times theta, but this theta now is in degrees, so you simply multiply by the conversion factor pi by 180. And this will also now give you your arc length if this is in degrees. Alright, so now we have two formulas. No, you wouldn't necessarily need to memorize, well, you'll be able to look at your formula sheet, but if you could use either of these, okay, and it will be just fine. So we leave that for you to do. So next we look at now how do you do an example here. So let's do an example. So this example here says for a circle with radius 15.0 feet, find the length of the arc with a central angle of pi by 3. So it's given there. So the radius is 15 feet, 15.0. Your central angle is pi by 3 radians, and you want to find what the arc length is. So let's call the arc length S. So we know that S is equal to R times theta, where theta is in radians. Now we have both. We know that R is 15.0 feet, and we multiply that by theta, which is just pi by 3 radians. Now 3 into 15 goes 5. So the answer is just going to be 5 pi feet. Now if you plug this in your calculator and round to the nearest, well, if you look here, you see that there are 3 significant digits. So you should also round this to 3 significant digits, and you will get 15.7 feet, which is your answer. So our second example says, find the angle on the interior of the gear if the radius is 20.5 centimeters and the distance traveled is 46.5 centimeters. So you could see that what you're given here is just a circle. You're given that the radius R is 20.5 centimeters, but the distance traveled, which is really along here, that's your S value, is equal to 46.5 centimeters. Now what you don't know is theta. In the previous example, you knew the angle and your radius, but now you know the radius and S, and you want to find what theta is. So let's do this. So what you're given here, let's go through this together. You're given the R value, which is your 20.5. You're given the S value, and you want to find what theta is. Now the formula you know is S is equal to R theta. S is your arc length, R is your radius, and theta your angle in radians. But you want to isolate for theta. Well, you divide both sides by R, you get theta is S over R. You simply plug your S value and your R value in to find theta, and you get 2.27 radians. Now, why did I round to 3 significant digits? Well, your radius and your S value, your arc length, are both 3 significant digits. So that's in radians. How do we convert it to degrees? Well, we take our radians, we multiply by the unit factor, radians in the numerator here, so radians in the denominator, and that's your unit factor. You multiply that out and you get 130 degrees. To make this into 3 significant digits, you need a bar over the 0 there. Now we're going to be looking at the area of a sector. But first of all, we have to remind ourselves what is the area of a circle. So the area of a circle, as we know, radius r, the area is pi r squared. So that's important. We're going to be using this now. So if you know the radius, you could find the area. So let's see how this is done. Now again, if you have a central angle theta measured in radians, we're going to do radians first, and then we'll just give you the formula for when you have your angle in degrees. So again, this distance here is the radius, and what we want to find is the area, the shaded part here, the area, I'm going to call it A, the area of the sector. That's different from this area. This area is the area of the full circle. Alright, so we're going to use a proportion again. Right? We could say that the angle theta is to the whole angle in radians, which is going to be 2 pi radians in the whole circle. That's going to be the same as the area of the sector is to the area of the circle, which is pi r squared. So to solve for A, we multiply those two. So it's going to be pi r squared times theta, and you divide by the 2 pi. Right? So now the pi's go, and you're left with r squared theta divided by 2, or half r squared theta. So that's the area of the sector. This is now A. A equals that. So we know that the area of a sector is going to be half r squared theta, where theta is in radians, as is said here. Now, in terms of degrees, you could do this on your own. The area is going to be theta degrees, right, divided by 360 times pi r squared. And you could see where this is coming from. It's the fraction theta over 360 of the whole area. So either of those would work. So now we're going to be looking at an example. Alright, so here are 2 examples. The first one says, in a circle with radius 36.0 centimeters and the central angle 60 degrees 15 minutes, find the area. So again, we know that our area, now this is given in degrees, so we're going to be using our formula for degrees. So it's going to be theta degrees over 360 times pi r squared. Now our r is easy. That's our r value there, which is good. Now we have to do some work on our theta because it has to be in degrees. Here it's in degrees and minutes. So we have to convert this to decimal degrees. So we go that 60 degrees 15 minutes is the same as 60 degrees plus 15 over 60, and that's now going to be degrees. And if you do that, it's going to be 60.25 degrees, because 15 over 60 is a quarter point 25. So now we have our theta value. So now it's just a matter of plugging back in this formula. So our theta now is going to be 60.25. You could take the degree, that's also a degree, so they cancel off, over 360. Then you multiply by pi, and r is 36.0, and you're squaring it. Okay, and if you do that, you'll get 681, and it's centimeters, so area is a square unit, so centimeters squared. All right, now we look at our second example. A circle has a radius of 3.2 feet. The arc length of the sector is 5.6 feet. What is the area of the sector? Well, notice something here. You're given the radius and you're given the arc length, and you want to find the area. Now, we know that the area is half r squared theta. Do we know what the radius is? Yes, that's the radius right there, but we need theta. We don't have theta, so we first of all have to find the theta. Notice we're given s, that's our s value. So first of all, we could use our formula s equals r theta and solve for theta. Theta is going to be equal to s over r, right? And we plug the value of s in, which is 5.6 divided by 3.2, and that works out to be, well, you plug this in your calculator. You could use a fraction if you want, which is the same as 56 over 32, which works out to be 7 over 4 radians. It's sometimes better to use fractions rather than decimals, because you will have less rounding errors. So if you put in your calculator 56 and divide by 32, then you will get your 7 over 4 radians. So now we have everything that we need. So we go back here and say that the area is half. We know that the radius is 3.2, so r squared, and then we multiply by theta, which we just figured to be 7 over 4 radians. Now this has to be now in feet squared, our final answer. So if you plug this in your calculator, you should get 8.96 feet squared, but we go to two significant digits because each of those numbers have two significant digits. So the area then is going to be 9.0 feet squared. So now let's talk a little bit about what we call periodic waves. So you've probably heard about an alternating current, something looking like that, keeps going on and on forever. Now, if you look at one oscillation, which is, say, an oscillation is, say, here to there, that's one cycle. So the time it takes to go from here to here is represented as t, and that is called the time, or the periodic time. Right? Now, the number of cycles per second is called the frequency. Frequency is a number of cycles per second. Now, there is a relationship between t and f. So t is actually equal to 1 over f. Also, f is equal to 1 over t. Now, this is something which is good to keep in mind, right? The frequency is 1 over the time, and the time is 1 over the frequency. So you could see here that you have the formula for the frequency, but we should add to that, if you manipulate the formula, that t is equal to 1 over f. So this one is used if you know t and want to find f. And the second one here is used to find t if you know f. Now, if a body is rotating, there's something which is called the angular velocity. Now, the angular velocity, well, let's put it here, the angular velocity. Now, velocity is normally distance covered per time. It's distance over time. But for angular velocity, it's really the angle theta divided by the periodic time. Right? Now, the angle really is your 2 pi radians, which is your whole circle over time. So therefore, we know that that omega is 2 pi over t, but we know that t is 1 over f, or f is 1 over t. So we could write this as 2 pi times f. So that's our angular velocity, which is what we have right there. Now, if you multiply a velocity by a time, you get a distance, right? Velocity times time will give you some distance. So the total angle, we're measuring now the distance in terms of the total angle swept out. So it's going to be it has to be equal to some velocity times time. Now we know the angular velocity is the 2 pi f multiplied by t. So we could say that the distance then is velocity times time. So the total angle, which is a distance, you multiply your angular velocity here by the time. So which is where we get this from, that the omega t is 2 pi ft. Now from there, let us look at two examples. Given f is 500 hertz, what is the period? So we know that the period t is 1 over f. So it's going to be 1 over 500 hertz. And you get 0.002, and time is measured in seconds. So that's our answer. Now this one says it takes 100 microseconds to complete one cycle. What is the frequency? So you could see that microseconds is a time, so that's time there. So we want to find what the frequency is. So we know that frequency is 1 over time. So it's 1 over 100, but micro is times 10 to the negative 6. And that has to be now in hertz. And if you plug this in your calculator, you're going to get 1 with 4 zeros, which is 10,000 hertz, which you can write as 10 kilohertz. All right? Now, for these this last page here, all these examples are the solutions are posted. Now, there's nothing new here. This is simply a matter of plugging values in a calculator for the most part, interpreting what you've given, what you want to find, plugging it in, turn the handle, out comes the answer. So I'm going to leave this as an exercise for you to do. And if you're having problems with it, then we could take it up in our seminar.